What's up, guys? This is me again, Sir Ernest, and today we're going to have an example that demonstrates Hamiltonian dynamics. So the problem reads, we find the Hamiltonian equations of motion for a particle in a central field. So from our previous discussion, the central field is associated with a central force, wherein the central force is only a function of the radial direction. This gives us that the force function is determined by the derivative of the potential energy with respect to r. Okay, and from our previous examples, we were able to determine the equation of motion using number one, using your Newtonian mechanics, and you also determine this equation of motion using the Euler-Lagrange equation. Okay, so the Euler-Lagrange equation for the Lagrangian for a central force motion is already given by your previous example. So that's equal to 1/2 m times r dot squared plus r squared theta dot squared minus your central force potential energy associated with the central force field. So from here we can determine the generalized momenta. Okay, momenta, because we are going to have we have two degrees of freedom, one in r and one in theta. Okay, so the generalized momenta will be in terms of r, so that is pr, and that is equal to the partial derivative of L with respect to r dot, and this is equal to m r dot. So this tells us the linear momentum PR along the r direction will be mr dot. So therefore r dot will be equal to p r over m. So this is your PR would be the linear momentum in the radial direction. On the other hand, we can also calculate the generalized momentum in the theta direction or theta coordinate. So this is equal to partial derivative of L with respect to theta dot, and this is equal to m r squared theta dot, and this is your angular momentum. So we can rewrite theta dot as p theta over m r squared. So therefore we can now rewrite the Lagrangian in terms of the generalized momenta and its corresponding coordinate. So this is L equals 1/2 m times r dot squared would be p r squared over m squared, right? And then this is plus r squared times theta dot squared, which is p theta over m r squared minus u r, and this is now equal to 1 over 2m of p r squared plus p theta squared over r squared, right? Yes, minus ur. So now our Lagrangian is now in terms of r, pr, and p theta. from a velocity, an explicit function of velocity, we now express Lagrangian in terms of position, coordinates, and generalized momenta. So therefore, the Hamiltonian which is sum of P I Q I dot for all I minus the Lagrangian. Okay, so this is now P1, which is R, so that's P R R dot plus P theta theta dot minus L. Okay, so this is now equal to PR times PR over M plus P theta times P theta over MR squared. Okay, minus the Lagrangian, which is minus this. So this is 1 over 2m. So let's distribute here. So for easier algebraic manipulation, so this is PR squared over 2m minus P theta squared over 2mr squared minus a plus u r. Okay, so therefore the Hamiltonian will now be equal to, that's PR squared over m minus PR squared over 2m. So this is PR squared over 2m plus P theta squared over mr squared minus P theta squared over 2mr squared. And this is P theta squared over 2mr squared. Then plus u. So you will notice here that the kinetic energy would be this one or this one. So this is kinetic and this is your potential. So as we expect, the Hamiltonian of the system is just the sum of the kinetic and the potential energy, and this is equal to the total energy of the system. Okay, so the equation of motion is now rewritten as, okay, let me put it here. Okay, so here the Hamiltonian is a function of R, PR, and P theta. So again, we have two degrees of freedom, so we have 4 equations of motion. Okay, so the first equation of motion is written as, in terms of R, so this is R dot equals partial derivative of H with respect to PR, which is equal to PR over M. Okay, while theta dot would be equal to partial derivative of H with respect to P theta, and this is equal to this is equal to this is equal to P theta over 2mr squared. Okay, so what does it mean? So the first two Hamiltonian equation of motion just verifies our previous results for the generalized momentum. So this is equal to this, and this is equal to this. Amazing, right? Okay, So now let's move on to the next equation of motion. So here we have negative PR dot. This is equal to partial derivative of h with respect to r. Okay, so following this we have derivative of u respect to r minus p squared, p theta squared here. So differentiate this with respect to r. So this is negative, of course, yeah, negative over negative p theta squared over m. They think that should be, it's supposed to be r what? Cube. Very good. Okay. Now simplifying this, we have, so remember this one is m r double dot, or this is negative derivative with respect to time of PR, which is, what is PR? PR is mr dot, which is negative mr double dot, and this is equal to negative p theta squared over m r cubed minus fr. Okay, so I'm substituting p theta from here. Remember here that p theta is mr squared theta dot. Substituting it here, then simplifying everything, we have mr double dot, and that is equal to mr theta dot squared plus fr, which is what we got using your Hamiltonian mechanics as well as your the Euler-Lagrange equation. Now let's see if this is also consistent with theta. So we know that in theta, this is negative p theta dot, and this is equal to partial derivative of h with respect to theta. Because h is not an explicit function of theta, therefore this is equal to 0. So what does it mean? It means that the total derivative of p theta is equal to 0, which, as we expect, and as you guess right now, p theta, which is equal to mr squared theta, is a constant. Okay, so remember again, this is your, come again, that's your angular momentum. Very good. Okay, so using the Hamiltonian equations of motion, we were able to show this equation of motion in R, and we were able to show that the angular momentum of a particle in a central field is conserved. Amazing, right? So very consistent with Newtonian mechanics and your Lagrangian dynamics. Okay, so that's it. Very simple, right? Perfect. So right now I'll say thank you for watching. I hope to see you again in the next video. Thank you for learning something today. I'll see you again. Bye bye.